welcome to this session on electricity reliability. My name is Elisa Graffi. I'm a senior advisor in environmental justice at Pacific Northwest National Lab. Before that, I was a professor at ASU working on energy transitions, particularly incorporating renewables sort of a large scale. And this is a session topic that is near and dear to the hearts of, I guess, everybody in this room and beyond. It's been a tricky one. We have three great speakers today. Simone Fobi, is that, yes? Rob Cirincione, back there, and Lena Roald over there. So let me tell you a little bit about each of them, but before I do that, let me tell you what to expect from this session. Each speaker is going to have 15 minutes to present, and we're going to let them do their presentations, not ask questions during that. And then hopefully we'll have around half an hour of Q&A at the end. So if you just kind of hold on to your questions, we'll be able to get to those. Simone is an applied research scientist at Microsoft AI for Good Research Lab. Her work leverages computer vision, remote sensing, and machine learning to address societal problems in climate change, food security, and humanitarian crises. She recently completed her PhD in mechanical engineering at Columbia, with her research focused on electricity demand analytics and prediction and energy system design. She's worked on multi-university collaborations that combine large amounts of electricity consumption data obtained from electric meters with remote sensing satellite imagery to infer electricity demand from the combination of the two. This kind of analysis is of interest to energy providers as they design energy systems to meet anticipated demand in the areas where electrification is happening for the first time. Before that, she was a research scientist at the IBM Research Africa Lab in Nairobi, where she was also focusing on electricity access issues and reliability issues. Rob, sitting in the middle of the room, is co-founder and CEO of Sunairio. He's an engineer who studied the effects of uncertainty on technology strategy at MIT, and then spent more than 12 years developing novel approaches to managing weather-based risk in the energy sector. Prior to co-founding Sunairio, he held senior roles in the trading departments at Constellation Energy and Boston Energy Trading and Marketing, most recently as managing director of energy trading at BTM. Sunairio's weather simulations account for correlations between geographic locations across multiple time horizons and for all key weather variables. When properly set in the context of regional energy markets, portfolio risks are faithfully revealed and quantified, not obscured by unrealistic assumptions. And that's their own language. I didn't make up that lofty, but it sounds really interesting. Lena Roald is an assistant professor here at UW in the College of Engineering. She is in the Department of Electrical and Computer Engineering here. Prior to coming to Madison, she was a postdoctoral researcher at Los Alamos National Lab, and she's also worked with the National Renewable Energy Lab in Golden, Colorado, to collaborate on joint research projects related to grid resilience. And most recently, she's been factoring in societal and justice considerations to the traditional analytical frameworks about grid reliability and resilience. She's contributed to a number of research projects with the U.S. Department of Energy and the European Union funding, European Commission funding. And her research spans several energy resilience and transition issues, including floating wind turbine technology, utility decision-making around managing wildfire risks, and incorporating renewable microgrids to increase power system resilience under changing climate pressures. With that, let us start with Simone.
You can get your slides up for you.
So Simone, I'm gonna stand in the back of the room and I'll be able to keep that.
Good afternoon, everyone. I'm Simone Fobi, and today I'll be talking about data-driven decision support for low electricity access settings. This work is mainly from my PhD work, which I recently completed just about 3 months ago. So still have my foot halfway in the graduate student role here. So every year, billions are invested in different energy pathways, be it electricity, transport, biomass. But for low access settings who are yet to achieve 100% electrification, the decision of how to spend resources becomes even more critical. And for this talk, I want to focus on the electricity bin and how we can use data to guide planning and investments. During this talk, I'll talk first about electricity consumption growth studies that we've performed to give you some context of the area and what consumption looks like. Then I'll work on predicting levels of consumption upon grid access to support technology placement or siting. I'll also talk about continuous electricity consumption estimation, so moving from levels of consumption to kWh values and why that is relevant for utilities. And it would be leveraging a lot of deep learning approaches and remote sensing approaches. So starting off with electricity consumption growth, we looked at data from Kenya and Rwanda, and this was in collaboration with our utility partners from those countries. Mainly, we looked at hundreds of thousands of grid-connected customers, some prepaid, some postpaid, between the periods of 2010 to 2020. We're lucky enough that we had some locations for the customers. At other times, we had district locations. And a few things emerged from looking at that data set. One, consumption is relatively low compared to a place like the US. For example, in Kenya, we observed that consumption might be around 30 kilowatt hours for a household, whereas here in the US, it can be around 800, 900 kilowatt hours a month. In Rwanda, it was even lower. And not only was consumption low, but we noticed that as the utility electrified more consumers, it was bringing in a lot lower consumers into the grid. And this has implications on cost effectively running your system and also how you design it. So to provide a bit more numbers there, to my right, I show you a figure where you look at consumption over time for different cohorts of customers. The red line shows customers who were electrified, grid connected rather, in 2009. The brown and, let's say orange and brown show customers who were grid connected in 2015. And you can see that the customers being brought in are much lower than those that were initially connected. What this suggests is consumption peaks sooner, it plateaus lower for newly electrified customers, and this is consistent across the other country, Rwanda, where we observe that. Given this context, one thing to keep in mind is the cost of a grid connection relative to other systems. So this is a rough estimate of the kilowatt hour price on different systems. For a grid connection that can support, say, 40 kilowatt hours, the price is in the cents per kilowatt hour. For a solar home system, which might be more suited for lower consumers, the price is a lot higher. Concurrently, for an energy provider to make that connection in a rural area, it might cost them about $1,500 to extend a grid line to a household in a remote area, whereas a solar home system might be a lot more affordable. So the provider wants to know, before they make the connection, what would the household use? Our objective here was to help them answer that question, or rather guide them to answering that question by giving them a sense of relative demand across different areas, and then they could go there and perform detailed surveys to get a better hang of it. You can imagine that if they were to answer this question across the landscape of Kenya, it will be very costly to deploy surveys across the whole space. But we want to be able to leverage satellite imagery to guide them as to where to go to perform more detailed studies to get better hang of consumption. So we broke it down into two questions. One, how effective are images from pre-electrification era in predicting levels of consumption for a household after they get a connection? The other question we wanted to get at is, can we leverage lower resolution images to support that prediction? Like I mentioned before, we were working very closely with the utility. So starting off in Kenya, we had hundreds of thousands of residential customers, mostly postpaid, grouped by building, but we only selected single customer buildings because with imagery, at least at the time, we couldn't get good depth estimation for depicting. We used higher resolution imagery, 50 cm, and we had one timestamp per location. So that caused a lot of attrition in our data set, just trying to do the right match of an image before the household received a grid connection, and matching that to their consumption after electrification. So we had this data set of about 20,000 pairs, mainly because of the type of imagery that we're trying to match. And just to provide the question a bit more simply is, if we take a building in an image and we have some type of model, can we tell whether this household will be a high consuming household or low consuming household? What we actually did is we first trained a model on building segmentation task. And the purpose of that is we wanted our model to understand what the landscape looked like, what are characteristics of buildings, are they small, are they mud roofs, are they whatever characteristics may exist. And having trained that first, then we can go to the subsequent question, which is, will this building use more or less electricity? So we trained our model with about 7 million buildings and then tuned that in Kenya and then moved to the second step of predicting consumption levels. While we do the predictions at the individual building level, we actually do some aggregation and share this at a 250 meter by 250 meter resolution, just to address privacy concerns. And also for decision-making purposes, the decision is not really made at the household level. It's more like what regions can be interesting for which technologies. So we return not only the probabilities of our predictions, but also the confidence of our predictions so that decision makers can understand how our model or how confident our model is with a particular region. And we had an API to be able to share that. The thing that kept coming up is, yes, we're looking at satellite imagery, but what exactly is being learned? Is it just pulling random things from the image and making a prediction? So we took 3 approaches to understand or interpret what our models were looking at. One of them is just asking the question, if we were to pull out a building from an image and just give the roof size and the characteristics of the building, you can think of like rooftop material, for example. How well will the model do before we add an image? So we developed a model to do that. The other approach is called GradCam. It's a gradient class activation map method that asks the question, which portions of the image are highly activated when making a prediction for a specific class? So when you're saying someone is going to be a high consumer, what is the model looking at? Can we visualize it? And when you're saying that for a low consumer, what is the model looking at? The third approach is what we call unpaired image to image translation. And the question there is, within an image, what can be changed within the image so that a classifier would switch its decision from this house is a low consumer to, or this house is a high consumer. And by asking that question and looking at what is added or removed from the image, you can see what is driving your prediction or your model in making that classification. So what are the takeaways from that experience? One is our best case model on the individual household received an F1 score of about 0.7. F1 score is harmonic mean between precision and recall. What this means is that predicting at the household level is very hard. But still, this project was of value because if the utility had said that, let's look at our historical consumers and assume that people that we electrify will use the same as our previous consumers, they will always estimate that future consumers will use the same, but as we saw initially, consumption is decreasing over time. So even though it's at an F1 score of 0.7, it's still better than if you were to make that assumption of historic consumption. We also observed that lower resolution predictions can still, or lower resolution presentation of the results rather, can still support decision making. We aggregated at different resolutions that correlated with surveys like MTF and observed good correlation, about 0.82 correlation for our predictions with surveys. Now, in terms of the explainability side, when we carried out those 3 approaches, we noticed that the building roof characteristics are the most important features within the image. However, when you add in the surrounding context to that patch, your prediction performance increases by about 4 to 5%. So moving on to the next section, which is, now that we've done a classification, can we actually go to the kilowatt hour value? And we decided to simplify the problem here. So we're no longer asking the question that given pre-electrification images, can we predict consumption after electrification? We're asking a question, when we look at an image in this year, can we make a prediction? And why that is valuable is that one, the utility, well, one, we can ask the next question. If we look at an image this year, can we predict next year? And the utility can use that to anticipate demand for the next year, even share that with other energy providers that might need that data. So like I mentioned, it's a KWH question, similar formulation, just asking how much is being used. Here we had about 170,000 residential customer buildings, so a lot more than our first data set. We also wanted to get at the question of what is the improvement in prediction accuracy as we aggregate to lower resolution. So we did some splitting to about 1 kilometer by 1 kilometer grid cells, and I'll show you how the results turned out. Standard machine learning approaches here. Okay. So on the individual building level, when predicting KWH value, one, we noticed very high errors. So 75% MAP or MAPE, however it's pronounced. But when you look at consumptions that are greater than 3 kilowatt hours a month, it actually drops. So what this suggests is that the model struggles to make good predictions where there's very low consumption. And that's somewhat understandable because you don't know if consumption is low because people are actually consuming or if there's nobody in the house. So there's some level of ambiguity there. Also, when you're, say, consuming 1 kilowatt hour and the model predicts 1.5, for example, the errors are a lot heavier than if you had 3 and it's predicting 3.5. We didn't notice any significant difference between the bands that we used. The other interesting thing is once we aggregated our results to a 1 kilometer by 1 kilometer grid square, you can see a lot of improvement just visually between the predictions and the true consumption. And showing them specifically in terms of numbers by kilowatt hour, you can see that worst case scenario, we're around 35% off, even for low consumption levels. But for the high consumers, or between 4 to 10, we're around 20, 30%. So this shows that this is an interesting strategy to apply for areas where it's difficult to either deploy your sensors fully, or you want some initial sense of what people are going to consume before you go out and build robust surveys to acquire that. So I think I'll end here for today, but I want to take a minute to acknowledge all our collaborators, my primary advisor, Vijay Modi, who supported me in this work. Thank you.
First of all, I want to thank Tracy Holloway for organizing this event and for inviting us to present. I really enjoyed listening to everybody speak today. And I think the thing that I really enjoyed is the diversity of backgrounds. I think what that speaks to is how multidisciplinary sort of the study of energy and energy systems is. And that's one of the reasons that I've enjoyed doing this and you know, having my career in this space. So Sunairio, we're going to talk about climate modeling for electricity reliability. And before I do that, I will introduce Sunairio, the company, which is only a little more than 2 years old. I co-founded it in 2020. And what we do is generate innovative solutions to climate modeling to help energy companies answer questions around weather variability. The leadership team draws from a number of different areas. So you heard a little bit about my background in energy. We also have members of the team who are climate scientists. In fact, one is in this room, Sean Ridge. Actually, he's a meteorologist who earned his master's here right here at the University of Wisconsin before completing his PhD at Columbia. And he also has experience working for an insurtech company. We have CTO who has a similar background. And for those of you who are not familiar with that term, insurtech is basically the application of big data and machine learning to make risk products, risk management products. So very applicable to what we're trying to do here. Okay, so I'm going to start with a pretty basic question for this talk, which is how do we define reliability in the context of electricity? And here's the way I think about it. It's having confidence in the quality delivery of electricity to meet demand at all times. But there's a lot to unpack in this sentence, right? So like, what does having confidence mean? Is that like, is it a numerical threshold? Is it a probability? And if so, how would you quantify that? What does quality delivery of electricity mean? Probably something around the frequency, and the voltage, things like that. And finally, what does it mean to balance demand with generation at all times? How do we think about that? How can we be sure that under sort of all circumstances and grid outcomes, we have enough capacity to meet demand? In order to do that, we sort of have to think about like, well, what are the threats? What would prevent us from being able to reliably serve an electric footprint? So on the left here, I have what I'm calling traditional threats to reliability. So record heat, right? Drives up cooling demand, big risk to reliability. In the bottom left, on the flip side, cold drives heating demand. We also have, this is depicting a storm and trees falling on a power line. That's another problem. You heard, I think earlier in a talk today, or at least I did, mention of proper maintenance of equipment. That would also be a sort of classic or traditional threat to reliability. Then we have pictures on the right that I am using to describe what I'm calling modern threats to reliability. So the top right is a limp windsock, so it's no wind. So I think historically, no one would think about a calm day as a threat to reliability. But in the energy transition, this is a problem. This is a big problem. Similarly, in the bottom right, clouds are a problem, big problem. And the intersection of low wind and high clouds is a really big problem, or maybe night and low winds, right? So like these are the challenges that I think, this is sort of the existential challenge that's facing utilities as they try to guarantee reliability going forward. This is the problem. How do we manage weather variability, the intermittency due to this in the energy transition? I think that's the way that I would frame the reliability, like the modern reliability challenge. Okay, so in order to sort of be able to answer these questions with confidence and quantify reliability, we need models. It's 2022. We can make models of this stuff with data. So we need a forward-looking model of all grid outcomes at appropriate likelihoods. That's the way we think about being able to quantify reliability. A number of challenges, and here on the right are sort of some solutions that we have come up with. So for example, first challenge is that with respect to weather data and historical weather data that we're going to use to inform our models, historically weather data was available at weather stations, which are typically located at airports, which is great if we're trying to build a model of an energy system where the weather is driven by weather at airports. And in fact, that works pretty great for electricity demand, because airports are sited near population centers and population centers drive demand. So all that works. The problem is that now we're interested in modeling wind generation and solar generation, and we do not necessarily put those near runways. We put them wherever the wind is blowing and the sun is shining and the land is cheap and we can connect to the grid. And that often is in remote places. So we need historical weather data that's not associated with airport sites. Solution there is to leverage climate reanalysis. You heard this morning from NASA about their reanalysis product Merit 2. And if you didn't hear that or you missed that talk, climate reanalysis is essentially a historical estimation of weather all across the globe and at many levels of the atmosphere. Second challenge We need to do this many, many times, right? Because we need to model all grid outcomes. We need to understand the extreme events. In order to do that with a physics-based system, it'd be extremely expensive, slow, and ultimately impractical for a business like ours. So instead, we use machine learning and Monte Carlo simulation. Finally, we need to do this for many locations because most energy systems problems are regional. We care not just about weather in Madison, but we care about weather in Madison and Milwaukee and Green Bay and Chicago all at the same time. That's affecting regional supply-demand balances and could potentially be a threat to reliability. So we needed to come up with a simulation framework that was optimized for high dimensions, and we were able to do that. Okay, so a little bit more about climate reanalysis. We use ERA 5 for most of our historical data. ERA 5 is the European analog to MERA 2. So this is the climate reanalysis product that comes out of ECMWF. There's 62 years of gridded estimates of historical weather, and importantly and relevant for our talk, they're informed by surface measurements, ocean buoys, balloons, and satellites. Satellites fill in a lot of the information, so very relevant. Couldn't do what we're doing without satellite data. And let's see, 26 million observations are going into this stuff. So ERA 5 in general helps us a lot, and it helps us understand historically what weather was in locations all across the globe. However, there's one big problem that we've run into using this commercially. ERA 5 data, like most meteorological data, is organized in snapshots in time, right? So if you can imagine each one of these grids, these cartoons, imagine that that's the weather data for a particular hour, particular timestamp, right? So we started October 5th, the 4 o'clock hour. And then the weather measurement for the next timestamp is a separate gridded file. And these are all different files, right? And so this creates a number of challenges for us. Everything we generally want to do is in kind of the time series domain. So when we start with data that's organized like snapshots, we need to figure out how to construct time series from all of this, which sounds somewhat trivial, but I can tell you it is annoying to do, and it's slow, and it's time consuming. And figuring out how to do this is enough of a hurdle. It was a big enough hurdle for us that you know, my perspective is I'd be surprised if many people outside of research institutions, you know, specialized, you know, climate data providers are doing much with this data because it is so cumbersome to work with. And so one of the first things that we did is built a solution that can generate time series quickly and via an API from this underlying climate reanalysis data. And actually today, I think is the first time we're publicly announcing that we have an API that can retrieve this data, and we're signing up beta users. I'm getting a yes from Sean that yes, we're ready to go here. So if you're interested in playing around with this data, either send us a note on the website or come talk to us, and we'll get you set up. But this was huge. Now we can put in a coordinate, a lat long, and we can get reanalysis data downscaled to that particular location and return it quickly. And so we can actually do work on it. So that kind of data feeds the scenario weather simulation. What is the weather simulation? It's a machine learning powered statistical simulation of climate using sophisticated data and methods like we've been describing. So it's not a physics-based model like NOAA maintains or the ECMWF maintains. And what are we able to do with that? We're able to solve a lot of the limitations of the physical observations and physical-based modeling. So we're able to generate 1,000-path weather simulations for any weather variable, any location, again, using that underlying data. This is global, it's hyperlocal. We have proprietary downscaling to any lat long. And importantly, we're doing this in high dimensions. So we're correlating weather in Madison and Green Bay and Chicago and Milwaukee. And we're doing that for multiple weather variables. So the cloud cover in Green Bay is correlated to the cloud cover in Madison, which is correlated to the temperature in Green Bay and the wind speed in Green Bay, and so on and so forth. So we can actually understand what's happening from a regional perspective, to be able to model regional demand, regional wind generation, regional solar generation. And by the way, if you were a wind or a solar farm owner and had interest in a particular asset, we can model your specific location so we can understand how your wind farm or solar farm is operating relative to the rest of the grid. Are you generating when power is needed or not? And how does that affect your revenues, your profitability? Also, the last point here, importantly, this accounts for climate change. So one of the other challenges is, and one of the things I was doing at sort of the end of my time working as a trader, when I was trying to figure out, what would happen, what should I expect for the next, 5 years or next 10 years in some location? Well, one of the easiest things to do is kind of take, the last 20 years of history, right? Just let's do a backcast and say, okay, if we had the last 20 years of weather, what would happen? Well, increasingly it became very uncomfortable using, weather data from 20 years ago to describe what would happen in the future. So we use pretty standard ML methods to measure long-term trends and incorporate those into our forward simulations. This is just a slide describing, the fact that we're correlating everything and reflecting that in the output. And this I've sort of also basically described, but again, it's just a cartoon of how we think about stepping through this model in order to get to a sort of quantification of reliability or generation reserves or even market prices. We start with correlated weather paths. Each one of those weather paths is an input to machine learning models of electricity demand, wind generation, solar generation. Thank you for the explanation of ML-based electricity demand models. That's great. We do similar things for load, wind gen, and solar gen. And then since we've got all these things operating at the same time, we can put them together and get supply-demand balances, which we can then make models of electricity prices or generation reserves. So how much generation will we have relative to load? This is an example case study doing this for ERCOT. Chose ERCOT here because the data is publicly available and free to present. So we simulated a 5-year period, 2023 to 2027, 1,000 realizations of hourly weather for many different locations within ERCOT so that we can model the system. We make assumptions of renewable capacity build out over that 5-year period, and then we apply those machine learning models to transform our weather sims to energy predictions. And finally, and most importantly, we can actually the likelihood of those cases we were worried about from the beginning, the low solar and low wind happening at the same time as high demand. And so this is just some high level results of that, but we can actually put numbers on this. And so if you start at the left, a little Venn diagram of high load and low solar, when is that happening? It's about 3% of hours. So now we can put numbers on this idea of reliability. If you were in charge of ERCOT reliability, similarly for low wind and high load, that happens much more frequently. And finally, it's sort of the intersection of the low solar, low wind. It's less than 1%. And you can do a lot more with this, and we do with our customers. This is just kind of a high level way of describing how we can put all of this together and quantify reliability in this context. Thank you.
All right, well, great, thanks. And I will already apologize because you can see I started making my slides based on other slides from a separate workshop. But yeah, we are not at September 7 anymore, but it is really, really great to be here. I very much appreciate the invitation, also being part of this session, super interesting talks. I missed part of the morning because I was teaching. So because I am here in Madison, I have this ability to kind of be many places at the same time, and that can sometimes be a curse. It's much better to be there and involved all the time. Well, anyway, so my name is Roald, as you heard. I'm an assistant professor here in electrical and computer engineering. And so we really come from, so in my research group, we kind of come from really the power systems perspective. in that we are working with utilities to understand some of the challenges that they are facing and the models that they might need to use. So we are really working with kind of more technical grid models, I would say. I mean, I'm so, you know, looking at how power is flowing in the grid and how we can optimize dispatch of generation. And also a lot of that is then risk modeling with respect to renewable energy, as we heard from Rob, but also increasingly we are worried about the maybe even more extremes where we are seeing really bad weather and impacts of that on the grid. So in some sense, what I will be talking about here is grid unreliability. So grid reliability also in the technical sense has a very, very specific definition. And we are all very used to having reliability all the time, meaning that when you stick your device into the wall, it will come out, there will be electricity coming out for you. But you know, how could this change maybe? And what are we trying to do? And what kind of models are we trying to develop in order to try and capture how that can be avoided? Yeah, so essentially what I will talk about are some of those new challenges for power system optimization, which I think about as capturing the environmental and societal context of the grid. If you just press
Yep.
oh, there you go. Okay, good. Yeah, so when I'm talking about optimizing the grid, the way we think about it is we have the electric grid. On here, I've put like a bunch of transmission lines. I mean, or this is the actual transmission grid in the United States. It goes across very large distances. The people who are operating those grids, they are thinking about different objectives, such as keeping electricity affordable, but also keeping it reliable. And if you can't see what is on this image, that is because it's an image of a blackout. It is a picture of the New York skyline in 2003, when there was a big blackout there. In order to make this system work, there's a lot of technical constraints that has to be satisfied. We have to make sure that we have power balance, as we heard from Rob, so that production and demand are the same and balance each other. But then there's a lot of grid constraints that are there as well. Like, for example, sometimes you don't have sufficient, you might have sufficient energy, but you don't have sufficient capacity in the grid to transport it from A to B, right? And so how do you actually then try to manage this grid? That is the question of optimizing the electric grid, which is happening all the time. You know, this is happening every 5 minutes or so in real life. If I just wanted, instead of talking about this very complicated model, I could talk about it in the way we think about it is in these simplified models where we are looking typically at the grid. You see you have generation that is connected at certain electrical nodes. You have loads, you have some renewable energy, you have some transmission lines. So what we're trying to capture in our models traditionally is this grid structure. And in particular, one problem that is of great importance is what we call the optimal power flow model, where we are trying to optimize how power is moving around in this network to prevent any of those lines from being overloaded. For those of you who are familiar with the Kirchhoff laws, you know that it is actually hard to manage power flow in a grid like this, because you have very little ability to really control the flow of power. What you can control is typically where power is being generated and increasingly to some extent where it is being consumed. So if I now think about grid reliability, what utilities are doing today is to try and make sure that like 99.9% of the time this grid is operating, and whenever you want to consume energy, it's there for you. But what we are thinking about also these days is how do we think about this type of optimization problem when or how can we kind of reframe this question of reliability when we are facing issues like renewable energy variability and climate change. And in particular, this becomes very important if we are not always able to provide the electricity at the point in time when it is needed. And that is, I mean, we don't want to be in that situation, but it is increasingly happening. And we can see in California, approximately every year, you will have times in spring where there is just a huge oversupply of electricity due to renewables. And then you come August, and you know the utilities will be calling for people to conserve power because there is too high demand. And so we are really facing not only at the day-to-day scale, but really also on a seasonal level, kind of challenges there. I mean, Texas, we had this deep freeze event where essentially a lot of the natural gas generation was knocked out, which caused huge power outages. And when we were thinking about it, if you look to Europe these days, the way that continent is also bracing for potentially rationing of energy throughout the winter, there is a lot of questions here on like how that maybe some of these things are just happening more frequently, and we might have to prepare ourselves for them so that we can actually manage those in a way that doesn't destroy the network or how we are using electricity. And in order to try and think about this, we really need to capture more than just this technical grid model, right? And so I think most of you are very well aware of that. But as power engineers, we have traditionally not thought so much about it. We're very used to thinking about this power flowing around in this network, but we're not so used to thinking about all the things that are interacting with it. And so some of the things that we know that we need is, for example, renewable generation, pretty well established. There's other parts of the environment around the grid that is also becoming increasingly important. And I will be talking about some of a little bit more details on our work on wildfire risk and integrating that into the grid model. And then you can also think about trying to capture more of the context as in the societal context, thinking about customers, different group of customers, how some people might be able to better cope with outages, whereas others might not be able to. And so these are kind of questions that we are trying to explore in our work. So through a bit of this, this risk of wildfire ignition and how that is happening. And in particular, how does the kind of grid actually cause higher risk of wildfire ignitions? And in fact, I'm working on a project also with Elisa. Some of the work that I will also present now is also with Noah and Sophia, who are both here in the audience. So yeah, just want to acknowledge that. So for many of you, I don't know how familiar you are with this, but electric faults, when there's an error, something bad that happens in the electric grid, there tends to be sort of sparks and arcing that is happening. And an arc is like something like a lightning strike coming from an electric line. Over there, you can see some sparks from a down power line. And what can happen is that if this happens, you can, and it's very dry and hot around the line, you can get an ignition of the vegetation that is there around the line. And such ignition events are unfortunately not very. If you look at statistics from, for example, PG&E, you can see that there are several hundred of them every year. In Texas, there's estimates that more than 1,000 fires are started yearly by power lines. And some of the most, so the largest and most destructive fires in recent history have been caused by power line ignitions. And the reason for this is that when a power line falls to the ground or there is a tree that touches it, it is often because of the weather around the line, that, for example, high wind conditions, which can both increase the probability of power line ignitions and also increase the probability that the fire will spread quickly and grow uncontrollable. And so here are some example statistics from San Diego County, where you can see that just 5% of fires are being ignited by power lines, but those fires account for 25% of the area burnt in the county. So this is just to say that this is an important question. And of course, we know that wildfire risk is projected to increase significantly in the future. So if you think about wildfire risk, we can think about it very simplified as some function of the probability of an ignition times the size and intensity of the resulting fire. This size and intensity of the resulting fire, this is where the connection to satellite data is coming in. So we are using, we've been trying to use data from the US Geological Survey, which is pulling in satellite data, for example, that is assessing real-time vegetation status throughout the United States, looking at things like how brown and dry is the vegetation, and also other kind of data in order to create this wildfire risk forecast for the entire country. And so why do we care about having access to this data? Well, of course, what is important to us is that it should not only be the utilities in California who's able, they are under very, very big scrutiny currently for having caused a lot of wildfire ignitions, we don't want the tools that we are trying to develop to only be available to Californians. We want it to be available to utilities across the country, and in particular also to small rural electricity co-ops that might not have 5 PhDs on in-house, right, to work look at this. All right. When we are looking at this, though, this is typically something that utilities don't really control. They don't control the weather. They don't control the vegetation in the wider area around the line. So they can typically control the probability of ignition primarily. So in order to reduce this risk of wildfire ignition, there are several things that you can do. Some of them involve things like infrastructural upgrades, vegetation management, and more frequent maintenance, which are good long-term solutions, but they do require quite a bit of implementation time, and they can also they often have a high investment cost. And so in order to prioritize where to do this, where to implement these long-term solutions, we have been looking at this wildfire risk data and develop decision-making tools to try and help utilities understand which lines are the best ones to choose for undergrounding. And Sophia is going to give a flash talk about this a little later today, so I will not talk more about that part of our work. I'll leave that for her. Then we also have another set of solutions, which are the more short-term solutions. And these are solutions that can be implemented very quickly. So if it's high wildfire risk tomorrow, I can do this right now. And the drawback of these type of solutions is that they tend to be quite disruptive. So you might mitigate wildfire risk and they might be fast to implement, but they actually contribute to reducing electric reliability. And the most sort of disruptive of them all is what we call a public safety power shutoff. So a public safety power shutoff is a situation in which a utility decides to shut off a power line to remove the risk of ignition. Because if there is no voltage and no current on a line, there will not be any of the sparking and arcing type events that cause ignitions. However, if you shut off a power line, it will also cause power outages because some people rely on that line in order to get electricity to their house. And so kind of the largest such event to date was in California in October 2019. This is a newspaper clipping from that, where approximately 3 million people lost power. But after the utility went out and inspected the lines and looked at what had happened during this high wind event, they said that they found that there were 100 potential wildfire ignitions that were avoided. So 100 incidents of damage to the grid that could have caused an uncontrollably large fire. And so this is like really the trade-off that we're facing here. And so the question that we've been trying to ask ourselves is, can we do better? And so this is where we've been looking at trying to develop these mathematical decision-making tools. I'm not going to go through this in very much detail, but essentially the idea here is that we create these mathematical models where we are looking at things like trying to maximize the amount of electricity that we are able to deliver to customers versus the wildfire risks that we have to accept. And into these models, we can then integrate a lot of different things. And also, for example, lots of equations that model how the power system operates when we choose to make those shutoffs. And essentially what the connection here to the rest of everything is that trying to determine what the parameters of these models is can be really hard. And that is where, you know, we are very happy that there exists such data sets and on wildfire risk and so on, and the ability to leverage both remote sensing and also in combination with local sensing to try and get better assessment of this. Because if you have that data, you can then make better decisions. Yeah, and this is just an example of when you have this type of model that I just showed you, you can start asking questions of, for example, what is this trade-off that I'm willing to accept between causing power outages and allowing for wildfire risk in the grid? And essentially here we have parameters that allow us to vary the risk and decide how large of a power shutoff we are willing to accept. So for example, if I'm willing to accept a higher wildfire risk, I can serve more power to people. But if I really want the wildfire risk to be low, then I might have to take a pretty large power shutoff. And these are important trade-offs to be able to analyze. Yeah, and then I think I have maybe 20, 30, yeah, a minute or two left. So I just wanted to also, since this is also, we have time for discussion here, I wanted to just talk about some other uses of satellite data that I'm thinking about in our work, because clearly we are not satellite people. But yeah, one example is post-disaster assessment and restoration. And so, for example, in this wildfire risk problem, one of the things that happen that causes these power outages to be very prolonged is that people have to go around and try and figure out like what's their problem with the line or not. So that is part of it. You have other situations where you have like really physical damage to the grid on a large scale, like this is Hurricane Ian in Cuba. And here, of course, I mean, you can then think of things like trying to understand which areas are hardest hit using satellite data, right? So we are very interested in understanding also these type of questions of where should you try and invest your resources to bring the grid back up again in order to try and bring power to the people who need it most as quick as possible. And so one thing that we are doing is that we are trying to develop algorithms to help utilities decide on what would the optimal restoration strategy be. And one of the things that we have shown also in our work is that if you have solar PV distributed throughout the feeder or throughout the distribution grid, it really changes what is the best way for you to think about restoring power to people, because it means that some people already have access to power and they might maybe be okay, while other people might need power more urgently. And of course, for utilities, keeping track of exactly where those solar PV installations are is hard. And yeah, here is just a picture where, I mean, we heard about rooftop materials, right? And so this is also one way you can think of leveraging this type of data. And then finally, I mentioned also in the beginning, societal context. One of the things that we are very interested in, also talking to Elisa about, is that we are interested in trying to understand, how do we not only account for power in terms of kilowatt hours and megawatt hours, but also trying to dive more deeply into how does it impact people, what are customers' vulnerabilities. And so this is very new work and ongoing work, also inspired by a lot of geospatial data that is not satellite data, but typically census data based. So just a brief summary here. As I have tried to do, the key takeaway here is that we are trying to incorporate more information of the context around the grid in our grid models. There are different ways when we are talking about optimization that this information can enter. It can change what we are optimizing for, because when you solve an optimization problem, there's always something that you're trying to maximize or minimize. It can help us define better constraints. And another thing is that it's very important for us to think about, I mean, particularly engineers who are maybe used to think about our research as being very sort of objective. That actually, based on which test cases and metrics we choose for evaluation, we can get very different outcomes in terms of what seems to be good methods and bad methods to use. This was just, we are putting out, this is just an effort that a paper that we are hopefully submitting tomorrow or today on trying to provide geospatial grid data, which we are hoping to leverage then along with other geospatial data to make better analysis tools. So this is the California infrastructure. And we also have our whole code base available if anyone would like to test this out. So thank you. So maybe just want to come up and take the front. Let's see how that goes. Okay, thanks. So questions, comments?
I guess this is more for Rob. How important is your technology or your work for offshore wind versus onshore? Does it matter? Does the variability matter as much offshore as it does onshore?
Well, I think it's very important because back to the point of where does the data come from, right? So if you're limited to land-based measurements, you're gonna have a really difficult time doing the resource assessment. So I think this kind of technology is huge for any location where it's difficult to get good weather data. And to your point on variability, typically offshore is less variable, right, than the onshore stuff, but there's still a ton to understand. And so I think importantly, it's like, we're working with customers that are asking us questions like, okay, I own, these types of resources right now, some onshore wind, some onshore, some land-based solar, obviously. What should I add to my portfolio from a reliability basis or from a profitability basis, right? And so should you be spending the money on offshore wind? Does that make the most sense? Or does it make sense to do something more conventional, even though it's more variable, it might be far less expensive. And so I think those are the kind of trade-offs that we can answer.
I saw somebody else's hand over here.
I have a simple question, and then I'd like to follow up on a broader one, and it's to Elaine. What causes the electrical faults? I mean, what is there being done just to mitigate electrical faults?
Yeah, that's a really good question. Well, electrical faults are kind of like inherent thing. I mean, things can break and that is because it can break because of old age. It can break because of bad maintenance. It can break because of many bad reasons. But the
Load imbalance.
so it's more like, I mean, one of the Paradise fire in California, the campfire that burned to
Right.
Paradise was caused by a hook on a transmission line that was 100 years old and had just not been switched, like been replaced. And so there can be it's components that fail. It can also be the Dixie fire, which is a very, very large fire. It will happen because a tree fell onto a power line. And so there is a number of reasons why this can happen. Sometimes it can just be that it is windy and the lines that sort of like they move and they hit each other, and they're not supposed to do that. And it shouldn't happen too often, but it does happen. And part of it is that and why do we allow that to happen is because otherwise it would be very expensive to build the whole infrastructure so it's completely failproof. So it is like a kind of an economic consideration in how much do you invest in making it, avoiding the faults versus how much do you maybe accept that might happen.
And I guess my follow-up question, and again, I'm a satellite guy, but I'm going to ask a question about in situ measurements. It doesn't seem like it'd be that large of a cost to possibly have, net stations at these towers, which is going to help address, ERA 5 is a certain scale that's not capturing a lot of the variability, and it would give you some more immediate way to be, mitigating these things. Is there thoughts about that? I know that like wind farms do have met stations, and in fact, we're assimilating that data.
Can you guys in the back hear the question? Yeah, okay.
So yes, absolutely, but we have a very short time period of that data. So that's generally the problem that we run into, right? Because we're trying to help customers understand, what are the extreme events, and typically in high dimension, right? So like, what's the chance of having a low probability event in these two weather variables across this region? And if you only have a couple of years of
Right.
history, you don't have a lot of confidence in that.
From a power perspective, maybe just the power lines are hard to I mean, they are just very long. It's like, thousands and thousands and thousands of lines, and there is a tower every so often. So there's a limitation. I mean, there's some challenges in how many sensors can you place on this. That is actually one of the questions that we're working with collaborators to try and address.
There's a question here.
Yeah, so I have a couple of questions, if I may. So to Simone, I'm wondering if you can expand a little bit on explaining why you're seeing lower electricity demand over time, and is it only purely because you're expanding into areas that are lower and lower income, or there are other reasons for that? And then to the other two speakers, I had a question on whether, in fact, I mean, you're seeing, of course, that with renewables, the climate variability has a big impact, as you mentioned. But then at the same time, to reduce the risks of some of these sort of like wildfires and other kinds of risks, having more renewables in the system might be better. So like this, have you considered this particular trade-off or synergy in a sense? I'm just curious to hear from the people on that.
Start with Simone.
With respect to lower demand, I think it's a combination of different things. One you mentioned is going into more rural areas with lower income families that don't necessarily own the appliances or the ability to purchase the appliances. The other thing is that comes into play is also efficiency, appliance efficiency. But the challenge that researchers have had is quantifying the proportional contribution of each, which usually comes maybe from surveys. Unfortunately, from the utility standpoint that we've been working with, beyond just what they see in the meter, there's not much metadata there. So we've struggled to be able to decouple that. We've looked preliminary at some surveys from Rwanda, like EICV, but the challenge with EICV is they're not geolocated. So now you have the other problem where you can't tell what's what, yeah. But hopefully, Professor Modi is hoping to deploy a survey in January that can combine both and separate the contribution.
So you guys can choose who goes first on the second question.
Well, sure, yeah. Okay, so question of renewable energy and reliability and how those interact, right? So, I think it's super fascinating. These new modes of kind of challenging operating scenarios that are happening also. And you know, also how frequently. I mean, one of my questions for you is like how extreme of scenarios can actually machine learning give you in this kind of simulation. But when we think about from the reliability perspective, it is kind of interesting, right? I mean, on the one hand, we are putting the generation in more remote areas where there's sun and wind, but oftentimes it also comes closer to us. It can be on the rooftop and so on. And so having distributed generation throughout the grid is in particular when we are facing those situations where maybe part of the grid is down, it can be a big bonus. And in the electric power system community, we refer to that as resiliency, because we think of reliability as like everything is working, but the ability to continue to operate at like half operation is a lot about having a more resilient energy system that can respond. It is a really, really big bonus if you have this geographically distributed generation. And of course you still face then the issues that there will be a night, there will be a day without wind, but yeah.
Well, the thing we didn't mention is storage, right? And so I have every confidence that we're going to have a decarbonized grid, and we're going to get there through a combination of, wind and solar and storage, and that's one of the applications for our technology that we're seeing, because, storage, battery technology, or other, types of storage is great, but that by itself doesn't tell you like where to put it or how large to size it, or how to schedule it. And so we're doing that work as well to help companies understand, well, these are the durations of events that you're going to experience. This is how likely, and therefore, this is sort of capacity or location that you need for different storage. So I think that's a big part of the mix.
I'm glad you mentioned that. I noticed that none of you talked about storage. And it seemed like
it's hard. Storage problems are really hard. Like just really hard. That's my personal perspective from working on and I haven't done a ton of work, but from the little that I've done, it's complicated.
I also find it kind of maybe just as a follow-up on that is that storage can help solve some problems, I think, but there's also this question of like how much is actually reasonable to have and over what time horizons can you have storage. And of course, there's things like pumped hydro that can store energy seasonally, But if you're thinking about a battery energy storage, you will not fill that in April and discharge it in August, right? And so there's some scales. I mean, California curtailed 535 gigawatt hours of energy from solar and wind in April. That is equivalent to running 2 nuclear power plants, big ones, for 17 hours a day on max. And that was just lost energy, right? And then in August, they don't have enough capacity. And so I think, even if you just need such an amount of storage to capture all of that, I mean, maybe we will get there with electric vehicles, right? As partially, maybe we will have this ability to kind of multiplex some battery energy storage, and we will all become more flexible. But yeah, I mean, I think it's a super fascinating problem.
And I think one of the biggest storage resources we have that we would need to replace in the fully decarbonized futures is the longest duration and the most challenging, which is natural gas. Right? So like, we don't really have any proven technology out there that can come close to what we're going to need to satisfy seasonal heating when we get rid of natural gas. We put an enormous amount of gas in the ground in the summer just to then use it for heating in the winter. And when we electrify to do that, there's nothing that, the only thing that, I think that looks just kind of, the only thing that makes sense right now is that in theory, we would replace natural gas with hydrogen. And you use hydrogen to then power, combined cycles and stuff like that. But short of that, I don't think that's one of the big challenges out there.
Yeah, just one of the things about the ERCOT example is that for anybody that says, well, we'll just have natural gas as backup, and then the ERCOT situation is natural gas failed too. So,
yeah, well, what's interesting is natural gas failed for companies that didn't have firm supply of natural gas. So ERCOT kind of failed itself. And what I mean by that is there was never a mechanism in ERCOT for power generators to be responsible for operating at all times. That was one of the key differences of ERCOT. In every other organized electricity market, there's a mechanism that it's called usually a capacity market. And you have to prove basically that capacity you own will operate at any day of the year. And ERCOT never had that requirement. But gas is reliable, has been reliable for heating. So if you go back to like the 2008 polar vortex event, right? Very cold, all over a huge swath of the country. But what you didn't hear about from that event was people saying, oh, my gas utility cut off my gas to my house. I didn't have heat. Everyone had heat. We can solve that problem. It's just bad policy in ERCOT.
I see. Lena, you look like you have something to say.
Well, yeah, well, they curtailed the generation, right? They stopped producing gas power, and it is right. I mean, part of it is also that natural gas. If you lose pressure in the natural gas system, it can take years to come back because it's extremely hot. Natural gas gets explosive if you get air inside the pipes, and so it's just super dangerous. But yeah, it's right, it doesn't happen at a large scale, so it's fascinating. Yeah, I mean, it is quite reliable, I would say. I agree with that.
Great. So Lena, you mentioned nuclear. I think you're the only one that did, and you mentioned it briefly, but let's see. So nuclear, it's kind of experiencing something of a, I don't even know, comeback is not the word I want. It's getting a lot of attention with this administration because it's clean. And what is it? It's like, I don't know how much natural gas, produces, but nuclear is what, like 20% or something of the electricity mix. But is there a role for that when you're thinking about the synergistic, the mixes? Is there a role for nuclear, or is it really natural gas and renewables?
I think nuclear makes a ton of sense. Like, I mean, I don't know why people were trying to turn off nukes over the past couple of years. Seems like priorities should have shifted a little bit. That's just a personal opinion.
There's also a lot of development on the nuclear side to make it. So one of the benefits of natural gas is that the generators can move up and down, right? They can respond to changes in renewable energy, for example, very quickly. But then nuclear power plants are much slower to move up and down in terms of their energy output. And so, but yeah, there's exciting research also in that space to try and make them more flexible so that they can also start providing more of that need. I mean, I kind of also, I personally agree with the fact that I think we need the low carbon energy sources we can get if we are gonna make this transition work. But yeah, there is of course a lot of challenges with nuclear, and I will just say, like, currently in Europe, France is a country that has betted very, very heavily on nuclear. They are currently experiencing that all of their latest generation nuclear power plants have cracks in the containments for the inner circuit. And so they don't know which of the generators have that. So they have to shut them down one by one and check. And that means going into, an extremely radioactive environment. And it is taking a lot of time. And it might be contributing to France having about half of the nuclear capacity that they normally have during this winter. I mean, they don't yet quite know how much they will be able to check and get back online again. And so these are, there is, and then, yeah, I mean, I guess we are doing something good at UW to try and educate nuclear engineers because there has been a lag of that, I mean, the number of people. So if there's anyone here in the nuclear engineering program, kudos to you. I think it's really important to keep the workforce up to date. So
I'm gonna go back to the room. I just want to say that like the conversation that you guys just had could take us completely in the direction of comparative risks and comparative safety of different mixes and scenarios. And let's see. Hang on for just 1 second, Brad.
Yeah, I had a quick question. My name is Jennifer McGinnis. I'm in the Holloway group. I wanted to say that I loved all of your guys' talks, but I had a follow-up question about when you said you have complete confidence in a decarbonized grid. I've also noticed a lot of public hesitancy to having a completely renewable grid, just because people point out like California that had rolling blackouts. So would you have any advice to getting better backing from the public?
Well, certainly events like brownouts don't help.
Yeah.
But I mean, I'm thinking over a longer time horizon, right? Like over a decade to 2 decades, we will get there. I think also, touting new technology, innovations in storage and things like that. And, putting forth good policy, good energy policy, good industrial policy, like these things help. I mean, I do really think there have been examples of just really bad policy that have created some bad results.
Mhm.
But I think the technology is there. And honestly, the electric grid that we have is a modern engineering marvel. Like it is. The fact that, as whoever said, like you can just plug your device into a wall and it works. We take that for granted, and it is really complicated what's going on behind the scenes, all this power flow modeling and optimization and scheduling that's happening. So, as someone who sees that and knows how sophisticated that is, and I think has kind of an idea for the technology that's coming down the horizon. That's what gives me hope and optimism. But yeah.
Yeah, thank you.
Can I make a very quick comment? Sure. One thing I think is so cool is that 10 years ago, people said like the grid cannot take more than 30% renewable energy. Like, yeah, bam, we're like way past that, right? At least in parts of the world. And it's just like, yeah, so the short-term things, and maybe we're still playing catch up, I think, on some of the other.
So I was just thinking that I'm thinking back in like 2014 is the year I remember people were saying the grid couldn't take more than 12%. So it's actually been changing quite a lot. It's hard to predict where it's going to go. I think we have about 2 minutes left, and there were a couple. Who had additional? Go ahead.
Hi, I had a question for Rob and Lean. My name is Thomas Lavery, and I represent an environmental organization on campus. For Rob, I was wondering, what kind of solutions, either short-term or long-term, would you recommend for areas where there's maybe low opportunity for solar power and like low wind, but also high demand for energy? And for Lean, I was wondering if your models, because ostensibly they were developed for like US grid systems environments, are they easily like transferable to other countries, or would you have to make specific changes to certain variables to account for like local vegetation or technologies in the grid system?
Well, one of the miracles of the grid is that, you know, if you're part of a regional grid, like we are here in the Eastern Interconnect, power, you don't get to control really where power goes. Like it's going to go where it's going to go according to the physics that Elaine knows. And so if you happen to live in a pocket that I guess is, you know, not renewables dense, I think there's still ways you could still participate in programs where you are, you know, causing the development of new additional renewables, which might not be located on your roof, but could be located, you know, 100 miles away, still part of the grid, and in a way that, you know, you're still causing a positive impact.
Yeah, yeah, so to the grid models, I mean, much of like the underlying physics of electricity are the same everywhere, right? The structures on top of it, how the market works, in some cases, how it's built, it can vary. When it comes to wildfire, for example, we focused on like data in the US, because we're in the US, but we're also talking to people, for example, in France, about their wildfire problems. And then, you know, I mean, but as you are going, kind of, I mean, geography does really have a big impact on the grid, and then as does also what we heard from Simone, right, about like energy access and expansion of the grid, which is, you know, that is a kind of a quite different paradigm potentially for a grid. And I would actually love to hear from you, because you mentioned these like as in-home solar systems, and versus a grid connection, and how one is cheap to install but expensive to use. Do you know, I mean, that is a completely different question, right? So if I could ask a question, I would ask
This will be the last question.
okay, what is being built out? Do you see many of these like small systems or more grid connections?
If I may answer
Yeah.
part of his question first, I think part of it is also about the type of data that can support certain models. So from my observation in the US, there's very high resolution 15-minute data to perform some of these analysis. Now, in the context that we're working on, even for households, getting meter data at the monthly resolution, it's good enough. Or not good enough, but that's where we're at. So to be able to run those models, one is either you increase the resolution of the data that you're getting, or start to rethink the models that have been developed to suit the data that you have. So in terms of transferability, I'll say the data format, be resolution, frequency, geospatial distribution is what would probably drive your analysis. To the second question, which is what are our observations? I think typically electricity access has been granted by utility, usually a single utility in a country. But what has emerged is that it can be very expensive for the utility to go into rural areas. And as Professor Shonali had mentioned in an earlier session, it brings up questions around new business models of how should we give access to people. And so we've noticed a growth or spike in centralized grid options where people are considering mini grids, solar home systems. And the question there is, one, how much does it cost to install a mini grid? What is the recovery period? How much will they consume versus a solar home system? If we put it in, will they actually use electricity? So that's why understanding where a household is in terms of consumption and how they will change would sort of drive which technology choice picks up the fastest.
Thank you. So we've actually come to the end of our time. I think there might have been a couple of other questions. Maybe the panelists will stick around for a couple minutes in case somebody wants to come up and talk to you afterwards. Yeah, but Lena, Rob, Simone, thank you very much. It's been a great session, and thank you all for attending and staying here for the good round.